what's up with it. So let's start with this one here. Example A, still section 5.4. F of x is equal to x squared plus 7x plus 12, and then over 4x squared minus 1. Okay? So before we do anything else, the very first thing we should always do for these is find the domain. And you're going to set the denominator equal to 0 in order to find that domain. Okay, so I'm setting 4x squared minus 1 equal to 0. And that's going to help me find my domain. Now I want to try to solve that quadratic by factoring if at all possible. Because it's going to help me when I go to simplify that fraction. Okay, so when I look at that, I see two terms with a minus sign in between. So I'm thinking that's a difference of squares. And the way I think about that is, okay, 4, what squared is 4? It's 2. And what squared is x? It's x. What squared is 1? 1. So then my factors end up being 2x plus 1 and 2x minus 1. That's definitely not the only way to solve this problem, but it is the best way if we know we've got to do other stuff. And we're going to do all of those asymptotes and things with this. Okay, so now we take and solve those. So we set 2x plus 1 equal to 0, 2x minus 1 equals 0, and solve those. So that's going to be x equals negative 1/2, and this one's going to be positive 1/2. So those are the things that x cannot be. So our domain is all x's as long as x does not equal plus or minus 1/2. I'm just shorthand that. That's positive 1/2 or negative 1/2. Either of those. It can't be either of those. So that's the domain. So we found the domain. Wonderful, great. Yippee. Set notation's absolutely fine for domain. We don't have to go to the interval on this because we've got so much other stuff to do. The interval notation for that would take a whole nother line and stuff. So now the next thing we want to do is try to simplify the fraction if at all possible. So to do that, we need to factor both the top and bottom. We've already done the factoring for the bottom when we tried to do the domain. Okay, so that's a shortcut is what this helps us do, is we got 2x plus 1 and 2x minus 1 on the bottom. We need to factor the top to see if we can cancel anything out. So if I'm going to factor the top, it's got 3 terms. So I'm going to do this x thing, multiply to be 12 and add to be 7. Numbers that do that be 4 and 3. So my factors be x plus 4 and x plus 3. Factoring the quadratic, that's that. If you learned it a different way, guess and check works the same way. Okay. So now we notice that the numerator and the denominator don't have anything in common. So we did all that factoring on the top and stuff really for nothing because nothing canceled out. But we got to check for that. We want to simplify the fraction if at all possible. This one doesn't simplify, so we're done trying to simplify it. So now we're going to go through and try to decide if it has asymptotes. Okay, so we're going to do vertical asymptotes first because most every one of these has vertical asymptotes. If it's simplified out to where there was nothing on the denominator, that would be the only case where you wouldn't have vertical asymptotes, is if everything in the bottom canceled out. And that's not going to happen too often. Okay. So the vertical asymptotes, because nothing canceled out, they match these equations that we got here with that. We just make them x equals negative 1/2 and x equals positive 1/2. Those are our two vertical asymptotes. And what I want to do is show you on the graphing calculator what that looks like so that you can kind of see where all this is going. Because the asymptotes really are just things that shape the graph is what they do. They don't really affect much as far as anything else goes but the graph. So with my graphing calculator, I'm going to graph that original rational function. So I'm going to y equals, and I'm just going to put in parentheses x squared plus 7x plus 12, close the parentheses, divided by parentheses, 4x squared minus 1. I'm going to hit graph. And if you look right here at -1/2, you see kind of how that is kind of hugging up against what, if you imagine the vertical line right there, this graph turns and kind of hugs up against it. Same thing here at +1/2. This side turns and kind of hugs up against it. That's what you can kind of see where vertical asymptotes are by looking at that, by looking at the graph. So we can see that makes some sense that there should be vertical asymptotes on each side because those are kind of spread out pretty good ways. All right. Now, the next thing that we need to do is follow our rules to decide if this original polynomial, or the simplified version really, has horizontal asymptotes or obliques, or neither of those. So we look at the degree of the polynomial. So what's the degree of the top, the numerator? What's the degree of the numerator? Well, it's 2. It's squared, right? Even a multiplied out, if you multiply this out, the degree would still be 2. The degree of the denominator is squared, so they're the same. Okay, so that tells us that there has to be a horizontal asymptote at y equals 1/4, because the number that's in front of x squared is a 1, so it's 1/4. That's where that horizontal asymptote is. We found that horizontal asymptote. Because it had horizontal asymptotes, what do we know about oblique asymptotes? Are there any? No, can't be. Horizontals and obliques do not occur together, so we know that there are no oblique asymptotes. And the reason that I bring that up, you might be like, why in the world are we trying to tell that there's none of these? Some of the final exam questions will have questions like, what's the oblique asymptote for this rational function? And it'll have several of them, and then it'll have a choice that says there is no oblique asymptote. And you know that by just knowing, hey, there was a horizontal because of the degree issue. So you just got to know those rules about the degrees, and that's going to help us find those things, okay? In section 5, we're going to find some other things that go with this, but we're going to focus on the asymptotes here in section 4. So let's go on and do another example so we see kind of some other stuff happening. Example B, g of x is x squared plus 7x plus 10 over x cubed minus 25x. All right. So the first thing before I do anything else is the domain. Okay. And how do we find the domain? It's what equals 0? The bottom, yeah. X cubed minus 25x equals 0. Set the denominator equal to 0, and then what method do we want to use to try to solve that? Yeah, factor it as much as you can, okay, because that's going to help us when we go to simplify the thing. So factoring is our key. So x would be a GCF, and that would leave us x squared minus 25. And then I know x squared minus 25 is a difference of squares, because that's x squared minus 5 squared. So that would be x plus 5, x minus 5. Those are the 3 factors for the denominator. And then that's going to make it easy to solve for the domain. We just set them equal to 0. X is 0. X plus 5 is 0. X minus 5 equals 0. And you solve those, and you get x equals -5, x equals +5, and then x equals 0. These are the things that x cannot be. Okay? So the domain for this one, x such that x does not equal -5, 0, or +5. You always find your domain before you simplify. Okay? Now, here's the thing you got to remember is don't lose track of these things because some of these, or maybe all of these, will be vertical asymptotes. Maybe all of them may just be some of them. Okay, depending on what cancels out when we go to do the simplifying. So the next step after you've done the domain is to go back up to the original problem and simplify or factor the numerator. So we've already factored the denominator. So I'm just rewriting the factored form of the denominator. So you need to keep track of your factored form of your denominator, bring it back up here, and then we need to factor the numerator. So we need something that multiplies to be 10 and adds to be 7. 10 and 1 would add to be 11. Only other way to multiply to be 10 would be 5 and 2, right? And those add to be 7, so that's the right pair. And because there's nothing in front of x squared, that means it's going to be x plus 5 and x plus 2. What cancels out? Yeah, the x plus 5 on top, x plus 5 on the bottom, because they're the same. Matching factors cancel each other out. So the simplified form for g of x is x plus 2 over x times x minus 5. That's the simplified version of that. Okay. Now, what's the degree of the numerator in the simplified version? Because this is what decides horizontals and obliques, is the degrees. Okay? What's the exponent on this x right here? 1. So the degree is 1 on the top. So the degree of 1 up top, put that degree. And on the bottom, 2, because if I say x times x, I get x squared, right? So that's a degree of 2 on the bottom. Okay? So the top is what compared to the bottom? 1 less, it's smaller. So if it's smaller, what do we know about its asymptotes? It's got a horizontal asymptote at y equals what? What was our rule about if the degree is smaller or less on the top than it is on the bottom? 0. You don't have to do any calculation to get there. You just 0. Since we have a horizontal asymptote at y equals 0, what do we know about the obliques? There aren't any. And remember, you will never have horizontal and oblique asymptotes both. What did we not find? It's actually pretty easy. Vertical asymptotes. I jumped the gun here. That's okay. Doesn't really matter what order you do it. Vertical asymptotes, we know every one of them should have some. What's left in the denominator to get vertical asymptotes from? These two factors. So let's get the equation. You set those equal to 0 and solve them. So it'd be x equals 0, and then x equals positive 5. Those two vertical asymptotes. If we looked at the graph of either the original one or the simplified one, they will be the same. I'm going to do the simplified one because it's shorter to type in. Be x plus 2 divided by parentheses. I'm going to go ahead and multiply that out to x squared minus 5x. X squared minus 5x. Just distribute the x. look at that graph's a little better. Your picture, we see more going on. You've got a vertical asymptote right here. We see these lines hugging up against that, the y-axis, which is x equals 0. That's where that vertical asymptote is. Then we have this one over here at positive 5, at that other vertical asymptote. And then we see, hey, it hugs right up against the x-axis too. Well, that's our horizontal asymptote at y equals 0 that cuts through the middle. Right? So we can see it kind of bends the shape of the graph. That's what the asymptotes do, is kind of shape the graph into what it really is. Okay? Not bad. Let's do one that's a little tougher. Let's do f of x equals 8x cubed plus 42x squared plus 45x minus 14. So an x cubed up top that's kind of big. And then 4x squared plus 11x minus 3 on the denominator. When you start looking at these things, you can decide about horizontals and obliques from either the original or the simplified version. Sometimes it's easier to see before you start factoring it all which one it is. So when we look at this one, what's the degree of the numerator? Cubed, it's 3. The degree of the denominator would be 2. So the top is how many more than the bottom? 1 more. So this is an example where we have an oblique asymptote. So we know before we go any further that on horizontal asymptotes, we can write none. Okay, we know it's not going to have that. We know we're going to have to do some long division to get that oblique. So this is going to be, it's one of the reasons it's a little tougher, because that long division's in there. Okay, so the first thing I want to do though is work on the domain. And again, that comes from setting the denominator equal to 0 and solving it, preferably by factoring. If the only thing that the problem asked you to do was find the domain, then you really don't have to do it by factoring, because you're not doing anything else after that. But for us on these examples, we're doing everything that you can on them. But if you were only asked to find the domain, you could solve that with quadratic formula if you wanted to and get the domain. But since we're doing some other stuff, we need to do it by factoring, because that's the best way to be able to do the other stuff. So 4 times negative 3 is negative 12. It's got to add to be positive 11. And multiply to be negative 12. So I'm thinking 12 and negative 1. And because there's something in front of x squared, I can't do the shortcut. I've got to go 4x squared plus 12x minus 1x minus 3. And then group those together. Now just take a little bit, practice on your factoring. If you're not great at it, you'll get there. Okay. And then GCF is 4x, leaves x plus 3. GCF of the second group is negative 1, leaves you x plus 3. So we get these factors, 4x minus 1 and x plus 3. Okay, so that's going to be kind of handy. We set those equal to 0 and solve to get the things x cannot be. So x can't be 1/4, x cannot be negative 3. So our domain is all x's as long as x does not equal negative 3 or 1/4. That's how I would write that domain. Now, this is where this one gets a little tougher, because it's a pretty big polynomial on the top. And if I'm going to try to simplify this thing, I've got to try to factor that dude. And that's not the easiest thing to do. So what I want to do is think about taking 8x cubed plus 42x squared plus 45x minus 14 and trying to factor it the way we did in sections 1, 2, and 3. Okay, so we've got a higher degree polynomial in the top. If it's just a quadratic up there, we know a lot of tools and stuff to factor that. But a higher degree polynomial, we don't necessarily have a ton of tools for that. So we've got to think about all the things we did last week with the first half of chapter 5. So the first thing that I would look to do, since it has 4 terms, would be group and see if it would work that way. If I grouped this one, first 2 together, what would the GCF of those 2 be? Of 8x cubed and 42x squared. Well, I know they're both even, right? So I know 2 goes into them. Is there anything bigger than 2 that goes into 8 that also goes into 42? Think about 4. Does 4 go into 42? No, that doesn't work. 8. It doesn't go. So 2 is the biggest number. And then how many variables do they share? This one's got x cubed. That one's got x squared. So that'd be x squared. And that would leave us 4x plus 21. Is there any way I could divide 14 by something and get 21? If I divide 14 by anything, it's going to get smaller, isn't it? So that right there tells me, hey, grouping's not going to work. You can't use that method. That would be my first try, though, because if it'll factor with grouping, so much easier than what we're going to have to do for this one, okay? So factoring by grouping would be, if it's got 4 terms in the numerator, that's what I would try first, okay? This one doesn't do grouping, kind of by design. I didn't want it to do grouping because I need us to make sure we can do that stuff from last week because it's part of our test for this next week, okay? So here's what I'm thinking. What's my first step in trying to solve or factor a higher degree polynomial? What's my job? What are the things we did? And I'm thinking synthetic division. That's what I'm thinking. Well, how do I figure out a number that goes on that shelf? Okay, the P over Q list. And then after we get the P over Q list, what do we do? Graph it. So I'm going to graph this polynomial that's just the numerator, not the whole fraction thing, but just that one. I'm going to graph that. And if I do my P over Q list or not, it really doesn't matter here. That is technically absolutely correct. You should do a P over Q list. But we're going to take that shortcut and just say, hey, I'm going to graph that dude. And get 8x to the third plus 42x squared plus 45x minus 14. I'm just going to graph it. I'm looking for some place that it crosses the x-axis at a good spot. And it looks like -2 would be that. So if I hit trace and -2, and I look at that, I get a 0 on the y. So that's what I'm going to use on my shelf is a -2 to break this thing down. So 8, 42, 45 minus 14. Okay. And so I drop the 8 down, multiply, and add. Let's be 36 minus be 26. Multiply, -52. That's -7. And there's that 0 in the remainder like I wanted. Okay. And what that does is it breaks that polynomial down from an x cubed to this blue line now is x to what power? Say it again. Squared. That's right. Yeah. Sorry. I was looking for 2 and you said squared and my brain didn't put those 2 together. You're exactly right. It's x squared there. So it's 8x squared plus 26x minus 7, which is a quadratic, and I can factor that using X method. So that's what I want to do here is factor that using X method. So so far I have x minus 2, or excuse me, x plus 2, because the factor is opposite sign, and 8x squared plus 26x minus 7. And I'm going to try to factor that quadratic that's left there. I'm going to factor it with the x thing. So 8 times negative 7 is negative 56. And it's got to add to be 26. So it's a pretty big number. The only bigger number I know that goes into 56 would be 28. And it goes 2 times. So 28 and negative 2. And that allows me to do the grouping stuff. 28x minus 2x minus 7. Now I can group that and pull out a 4x, x, and that'd leave me 2x plus 7, and then a minus 1, and that'd leave me a 2x plus 7. And now the fully factored form for this thing is going to be x plus 2, 4x minus 1, and then the 2x plus 7. A lot of work to get that factored form, but we've got to have that numerator factored so that we can cancel some stuff out. So this factored form that we've got right here, this stuff, is the numerator for this big polynomial up here. Shrink that down a little bit. And the denominator is the factored form 4x minus 1 and x plus 3. So all that work to get that factored form, but it pays off because something cancels out. 4x minus 1s cancel out. And in the next section, that's going to create a hole in the graph, which we'll talk about. It really is the easier part. We're doing all the hard parts in section 4. Section 5 actually gets a little easier because we've already done all the hard work. Okay, so now we have x plus 2 times 2x plus 7, and that's all over x plus 3. That still has an oblique asymptote. Okay, so when I look at that, I know it's got an oblique because the degree of the top is 1 more than the degree of the bottom. I've got to do some long division to get there. And here's the beautiful thing. If you don't simplify it and you do the long division correctly, you still get the same oblique asymptote. If you simplify it and do the long division, you still get the same oblique asymptote. It's just easier to do. The simplified version is much easier to do the division on than that big monster that we started with, because you got more exponents, more variables involved. We have less over here. The only thing I've got to do, though, is I need to multiply out this top part. X plus 2 times 2x plus 7, get 2x squared plus 7x plus 4x would be plus 11x plus 14. And then on the bottom, we got the x plus 3. That's what that thing simplifies to be. Okay. So that's what I'm going to do my long division with, is this smaller one, because it's so much easier with the smaller one. So the simplifying, it may be a lot of work on the back end, but it sure is worth it once you get to the long division to get the final oblique asymptote equation. So to do that, I'm going to take x plus 3 on the outside, and then I've got 2x squared plus 11x plus 14 on the inside. So when you do the long division, make sure it's in descending order on the outside and on the inside. And if there's a missing power of x, you put a 0 in its place. This one had every power of x, starting with the biggest one, the x squared. Plain x, no x's. It's okay. We didn't have to put a 0x in that place. Now, you look at the front. What times this x would get me 2x squared? Be 2x. 2x times x is 2x squared. So then I multiply 2x times the x plus 3 it's in front. So that's 2x squared plus 2x times positive 3 would be 6x. Put that in parentheses and subtract. The 2x squareds go away. That's what I wanted to happen. 11 minus 6 is 5x. Now I look at the front again. What times this x in the front gets me 5x here? A plus 5. Then I distribute 5 times x, 5x. 5 times 3 is 15. Parentheses, subtract. The x's go away. 14 minus 15 would be negative 1. This is the remainder, but it doesn't matter. The only part that matters when you're finding oblique is the stuff up top. That our oblique asymptote is y equals 2x plus 5. Okay. The oblique asymptote will always be in y equals mx plus b form. It will. That's an oblique asymptote is the slope-intercept form equation. Should always be that. The slope may be a fraction. The y-intercept may be 0, but it's a slope-intercept form equation always for an oblique asymptote. Let's look at the graph of this whole thing and see if we can kind of recognize this stuff. So clear that out. I'm going to use the simplified version, that 2x squared plus 11x plus 14 divided by x plus 3. Now we see right here at negative 3, we have a vertical asymptote, which we need to find. Nope. All right, vertical asymptote. Look at that part that's on the denominator. The only thing left is x plus 3, so we got a vertical asymptote. I'm going to abbreviate these in just a second. I'm trying to write that. At x plus 3 equals 0, and that'd be x equals negative 3. Negative 3. There we go. That's where our vertical asymptote is at. If we look at the graph, we can see this thing kind of straightening out here and straightening out there, right there at negative 3. You see that happening. We also see it kind of being this way. That's an oblique asymptote. That's what it's going to look like. If I were to graph my equation for the oblique asymptote, because I can, the 2x plus 5, you'll see it a little better. Look how it hugs up against that red line. So that's that oblique asymptote we're finding. So when you find your oblique asymptote or your horizontal asymptote or whatever, you can graph that and graph the original problem or your simplified version. They should be the same. That's how you can tell if you simplified correctly. Graph the original, graph your simplified version. If they don't lay right on top of one another, you did something wrong. Okay? So the graph is really going to help you there to check yourself. But then on the asymptotes, you can see what's happening there. If you look at the graph and it asks you, does this have an oblique or horizontal asymptote? Look at the graph. You can tell. You can see the ones that have obliques have a slant in them. The ones that have a horizontal one have they flatten out. You will see that in the graph. You should be able to kind of get close to where they are by just looking at the graph. So the graph is going to be, graphing calculator is going to be friend on that part. All right. Let's look at 5.5, which just adds a couple of things to this. Okay. And I'm not even starting another set of pages. I'm just going to continue here. So let's kind of go through the process that we're doing. So the first thing we're going to do is the domain. And again, we're going to do that by factoring the denominator. The second thing we're going to do is simplify. And we're going to cancel factors when we do that. Inside of simplifying, that's where holes exist only where factors cancel. If you don't have any factors canceling out, there's no holes in the graph. Okay? When you go to simplify, that's where you'll see where their holes are. And we'll see that as we do some examples here. And then after we've done that, we're doing our asymptotes. Again, vertical, horizontal, or oblique, whichever ones they have, and it goes to the horizontals go to those rules, obliques go to those rules, verticals, pretty much every one of them is going to have vertical asymptotes. Okay. Now the next thing that we're going to add here is the intercepts. What kind of intercepts can we have? What are the kind of intercepts that we look for in functions? X-intercepts and Y-intercepts. Those are the things we're going to look for. The X-intercepts and Y-intercepts. And then the very last thing is, does the graph cross? An asymptote. We'll see how we figure that out. Okay. All right. So a lot of the same stuff. We get a lot of things for free when we do it a certain way. It kind of helps us out. So we're going to look at some examples here. 1, 2, 3 examples that can help us in trying to get this this stuff knocked out. So the first example, let's just do f of x is equal to x squared minus 4 over x squared plus 5x minus 14. There's our rational function. So what's the very first thing that we should do? Find the domain. Okay, so let's do that. How do we do that? Denominator equal to 0. Very good. What are the factors? Multiply to be negative 14 and add to be 5. Good job. 7 and negative 2. Because there's nothing in front of x squared, I can take that shortcut and do x plus 7, x minus 2. Okay? Set those equal to 0. And there we get x cannot be negative 7, x cannot be positive 2. So domain x such that x does not equal negative 7 or 2. I'm going to use that factored form, x plus 7, x minus 2 on the denominator, and then I'm going to factor the numerator because the next step is to simplify. They won't always simplify, but we've got to try just to make sure that, because it's a fraction, and the whole the major rule with fractions is to always try to reduce it as much as possible. Okay, now that's a difference of squares up top. So how does it factor? X minus 2, x plus 2. Good job. That's wonderful because what do we see happening? X minus 2 cancels out. All right, what happens when you have a factor that cancels? What now appears in the graph? A hole. Okay, so we have a hole where x minus 2 is equal to 0. At x equals positive 2. We need to find the y value that goes with that. Okay? And you can plug that in by hand if you want to. I'm going to use the calculator to help me. Okay? Because it's so much faster. Okay? So, calculator, I go to y equals, and I'm going to, because I did the work there to simplify, I'm going to use the simplified version of this. So, my simplified version, the top part has x plus 2 in parentheses divided by parentheses x plus 7. And I'm graphing that. And then here's how you can use the calculator to find that one ordered pair. Hit trace, and then type in the x value that you want. The x value we wanted was 2, right? What is 0.4 repeating as a fraction? You may know. Shortcut for that. It's 4 over 9. If it's a repeating, one decimal place repeating, it's always that number over 9. So like 2/3 is 0.6 repeating because it'd be 6 over 9, and that reduces to 2/3. You can do it with the calculator, or you can plug it in to the function and do 2 plus 2 over 2 plus 7. And that's where the 4 over 9 comes from. I don't care which way you do it. You just got to find that ordered pair where the hole's at in the graph. Okay, so there's a hole at that spot because we had a canceling factor. If no factors cancel, no hole. Okay, those go together. Okay, now next thing to look at is decide, do we have a horizontal asymptote or an oblique asymptote with what's left? So what's left is x plus 2 over x plus 7. So what do the degrees look like? They're the same, so it's horizontal. We're at. It's the ratio of the leading coefficients, and the leading coefficients are 1 over 1. So the horizontal asymptote is at y equals 1. And I just abbreviated HA for horizontal asymptote. So I'm tired of writing asymptote. It's not a word that falls out of my hand real easy. Okay, so we know if it has a horizontal asymptote. What about oblique asymptotes? None. Yeah, that's a favorite answer. Okay, and that means we don't have to do long division as well. All right, so the next thing that we want to find are intercepts. Okay, so we're going to take the simplified version and we're going to find our intercepts. And you want to use the simplified version because it's smaller, right? So we got x plus 2 over x plus 7 is the simplified version. And to find, how do we find a y-intercept on any kind of function? What's the way you find a y-intercept? Make the x equal 0. So we plug a 0 in the place of x. 0 plus 2 over 0 plus 7, 2 7. So the y-intercept is at 0, 2 7. That's the easy one. Y-intercept should always be the easiest one because you just plug in 0, work it out. If you didn't use the simplified version, guess what the y-intercept would still be? 0, 2 over 7. If you happen to go back to the original and do this, it'd be the same thing. All right, let's do the X-intercept. A little bit tougher because how do you find an X-intercept? Make the y equal 0, which is taking this f of x and making it equal 0. So we're setting x plus 2 over x plus 7 equal to 0. Which actually turns out pretty easy on this problem because there's only one thing on the top and one thing on the bottom. If this were a problem that said like x over 5 equals 0, how would you solve for x? Multiply by 5 and it'd get rid of it, right? So the same thing up here. How do I get rid of x plus 7? I multiply by it on both sides. Works out real nice. And x plus 2 0 times anything is 0, and now I got x plus 2 is equal to 0. That's super easy. So my x-intercept is at -2, 0. You can always, take the top, the numerator, and set it equal to 0, and you don't have to show me all your work there. It's not super important to work it out there. You could table values would be a great way to look at it. Yeah, absolutely. You could do it that way. So yeah, a lot of them really easy. If you'll just look at the numerator of the simplified version and set it equal to 0, and like this one, super easy to solve. If it's a little more complicated, you might just look at the numerator graph and see where it's crossing the x-axis, like we did on example C in section 5.4, because that's how we were trying to find those things. Okay, so x-intercept, y-intercept, that's it. You may have more than one x-intercept. Not likely that you'll have more than one y-intercept, but it's possible with the rational functions to have more than one y-intercept. Not as common as having more than one x-intercept is, though. Okay, so just keep in mind you may have more than one x-intercept when you're doing this. It's possible to have more than one y-intercept. All right, so we've done a whole lot of stuff to this, but we're not done yet. We've got to look at it and see if it crosses the asymptote. What asymptote could it cross? It can't cross vertical asymptotes. It can only cross horizontals or obliques. Okay, we had a horizontal on this one. What was the horizontal asymptote? Y equals 1. Okay, so what we want to know here is, does this cross y equals 1? And in parentheses, I'm putting, that's the horizontal asymptote. That's where it came from. Okay. And the way to decide that is do it just like you were doing the intercepts, but instead of intercepting the x or the y-axis, we're intercepting the line y equals 1. So we set the whole problem, the simplified version, x plus 2 over x plus 7 equal to what the asymptote is, the horizontal or the oblique. Here we have a horizontal, so we're setting it equal to 1. Okay, that's where that's coming from. Okay, and then we're solving that. So the steps, now this is where really working it out would be more important, because we're dealing with something that's not part of the original graph. It's related to it, but it's not exactly table value type stuff. So we would set up x plus 7 multiplied on each side. That cancels it out there. And then we distribute 1, get x plus 7. And then what happens when I move the x's? They cancel out, don't they? Does 2 ever equal 7? No. So this has no solution. If there's no solution, can it cross it? No, it will not cross it. The only way it will cross it is if you get an answer for x. If you get an answer for x, then the answer to that question is yes. Okay. If your x's cancel out, the answer is no. It does not cross. Okay. Same thing happens if it's an oblique asymptote. You're going to set it equal to it and solve. You might have to do a little bit more algebra to get there. We'll do one of those here and see what happens. Let's do one like that. Example B. F of x is equal to 6x squared plus 9x over 3x minus 2. All right. Beautiful thing here is we don't have to factor the denominator. It's kind of simple. It's 3x minus 2. Nothing fancy about that. So my domain's much easier to find. I take 3x minus 2. There's no factoring to do, so I just solve it and get 2/3. So x, I know, cannot be 2/3. That's what I know about the domain. Beautiful, wonderful, great. I wish that's all they ask for. That'd be nice, wouldn't it? And there are some test questions and quiz questions where that's all it asks for is the domain. Okay, so we're doing all of these steps, but sometimes you don't have to do all of them. So be careful when you're doing your quiz and your test and stuff to read the problem and make sure you know what it's asking for. All right, so that doesn't satisfy everything. So we need to go ahead and try to simplify if at all possible. So I didn't have to factor the denominator, but I could factor the numerator to see if something's going to cancel out. So the GCF of 6x squared and 9x would be 3x, and that would leave us 2x plus 3. But that doesn't simplify. Nothing cancels out. So what's that mean about holes in the graph? There are none. So we know that the holes, there are none. Okay? Because nothing canceled out. The only time you'll have holes in the graph is if you got some factors canceling out. Okay? No factors canceled. So I really don't need this factor form anymore. I'm just going back to the original. If you want to keep it around just in case, hey, you got it. But I'm going to refer back to the original for everything. Okay. The next thing to do is decide about horizontal and oblique asymptotes. Well, hold on. Let's go ahead and find a vertical asymptote so I don't forget that, because I'm bad about forgetting that. Vertical asymptotes. Since nothing canceled out, our vertical asymptote is exactly the same thing as we found for our domain. X equals positive 2/3. So when you find your domain, you're going to have your vertical asymptote in there. You just got to simplify first to see which ones you keep for vertical asymptotes and which ones are gone. Okay. So vertical asymptotes should always match up to at least part of your domain. In this case, all the same as the whole domain. Okay. Now, horizontal asymptotes or oblique asymptotes. So we go back to the original. We look at the degree of the top and the degree of the bottom. The degree of the top is how much? 2 and 1. So the top is 1 more than the bottom. So that means we have an oblique. So it means we have none on the horizontal. So we've got to go through the work of getting the oblique with that long division. Everybody loves. But it takes practice to do it. So that's why I want to bring it back out. All right, so I'm taking 3x minus 2 and dividing it into 6x squared plus 9x. I'm going to go ahead and put a plus 0 there on the end to represent the the number that isn't there. Okay. All right. What times 3x would get me 6x squared? 2x. Distribute the 2x to the 3x minus 2. So that's 6x squared minus 4x. Parentheses around that guy and subtract. Subtract those two. The x squareds go away. 9 minus negative 4 would be 9 plus 4, which is 13x. And here's where it's a little tricky. What times 3 will get me 13? Or what times 3x will give me 13x? And the easiest way to think of that is say 3 times what equals 13. How do you solve that little equation over here? Yeah, just divide by 3 and it cancels out. Oh, the number that I need to use is 13 over 3. So I do plus 13 over 3 there. And then distribute if you want to. So that's 13x minus 26 over 3. Now, here's what the rest of that doesn't matter because it's the remainder. Just remember, oblique asymptote's just the slope-intercept form. We've got the slope and then the intercept there, so we don't really care what this remainder is. So I'm not even going to do that math because it makes my head hurt. So y equals 2x plus 13 over 3. That's our oblique asymptote. Okay. So we found domain, we found the vertical asymptote, the fact that there weren't any holes in this graph. We also found the oblique asymptote and the fact that there weren't any horizontal asymptotes in this graph. Okay. The next thing to do, excuse me, is to find the intercepts. Okay. To find the y-intercept, what do I do? Make x 0. So plug in 0 into the equation. Do the math. 0 over, it doesn't matter. 0, 0 is our y-intercept. It's at the origin. It's going to intercept, the graph of this thing runs through the origin. Okay, so we only had that one y-intercept. Let's get the x-intercepts. And the only thing you have to do for the x-intercepts, technically you're setting the entire problem equal to 0, but we know the denominator is going to go away. So if you'll just set the numerator equal to 0, you'll find x-intercepts. That's the shortcut that you can take. Okay. Where is the numerator equal to 0? And how you find those, you got all those skills. I could use quadratic formula on this. I could use a table. I'm going to use factoring because that's what we've been practicing a whole lot of. So I'm going to use it. 3x. That leaves me 2x plus 3. And then I set those factors equal to 0. And one of them ends up being x equals 0. That is the same as that one. Because what's the only intercept that can be a y-intercept and an x-intercept at the same time? It's the origin. That's why that shows up twice. And then 2x plus 3 equals 0. X is negative 3 over 2. So you get an x-intercept at negative 3 over 2, 0. And what the other one, the 0, 0, we already had listed, so I'm just not going to write it again. So there we found our intercepts for this thing. Okay, we didn't have any holes in the graph, but we need to decide, since we had an oblique asymptote or if we had a horizontal asymptote, we've got to decide, does this graph cross that asymptote? And you can graph it and look and see, but sometimes it's so hard to tell if it crosses or not because they get so close, and you could end up zooming in for days to try to find that one place where they happen to cross or don't cross. So the best thing to do is actually just do the algebra and work it out. So this is, let's do that. Fun part here. Okay, so what we're going to do is we're going to take the original function, 6x squared plus 9x over 3x minus 2. And I'm going to the original here because it didn't simplify. And I'm not using the factored form, so that's why I say original. So if you've got a simplified version, use it. This one didn't simplify. And I'm setting it equal to the asymptote, 2x plus 13 over 3. Okay? And I'm going to solve this equation. So I'm going to multiply by 3x minus 2 on both sides. That cancels it out there so that I've got, and I'm going to multiply this out. So that'd be 6x squared plus 13x, and then minus 2x, or not 2x, 4x, 2 times 2 is 4, and then minus 26 over 3. Combine like terms. What do we see happening here? Those are the same, aren't they? So when I move one to the other side, what's it going to do? Cancel it all out. So I'm going to end up with 0 equals negative 26 over 3. Is that true? Does 0 ever equal something else? No. So that tells us this has no solution. So we know f of x does not cross the asymptote. Okay, that's what this tells us, because we didn't get a solution. If you get a solution, it does cross the asymptote. Okay, if you get a solution. One more, we're out of here. Let's try to throw you a little curveball on this one. G of x equals negative 9x plus 3x squared over x minus 12 plus x squared. What's wrong with this thing before we even start? You gotta get to rearrange it all to where it's in descending order. So the bottom's in the wrong order, so there'll be x squared plus x minus 12. But the top's in the wrong order too, so I'm gonna rearrange it while I'm at it. And then what's the first thing I find? Domain. Denominator equal to 0. Factor it. Oops, this would be x plus 4, x minus 3. It multiplies to be negative 12, adds to be positive 1. So that's x equals negative 4, x equals 3. Those are the things that x cannot be in my domain. And then what do I do next? Holes. So to find holes, I've got to simplify. So I'm using the factored form. So that x plus 4 and x minus 3. And then the numerator, how does it factor? Take a 3x out. What's it leave in the parentheses? X minus 3. Good. What cancels? X minus 3. So that means there's a hole where? At 3. At x equals 3. How do I find the y value that goes with that? Plug it in. 3 squared minus 9 times 3 over 3 squared plus 3 minus 12. Working that out, be 27 minus 27 is 0. And if it's 0 on the numerator, I know the denominators doesn't matter. What number's down there? 0 divided by anything is always 0. So I've got a hole at that ordered pair at 3, 0. Is that right? I do that right. 3 squared is 9. 9 times 3 is 27. So 27 minus 20. Yeah, that's right. Okay. Hole at 3, 0. Now what? Okay. So we're going to have a horizontal asymptote at what? 3 over 1, which is 3. Yeah, the ratio of the leading coefficients there. Good job. So that means oblique asymptotes are none. That's great. We don't like oblique asymptotes. They're a lot of work. And then we got to do vertical asymptotes. Don't forget that. So vertical asymptotes or vertical asymptote. Which one? What is our vertical asymptote here? Remember that x minus 3 cancel out. So what's the only one that's left? The x plus 4, and its equation is right there. It's at x equals -4. There's our vertical asymptote. So we have a horizontal asymptote at y equals 3, a vertical asymptote at -4, a hole at the graph of x equals 3, y equals 0. That's a whole ordered pair that's empty. Now, next thing to decide are our intercepts. So I'm going to use the simplified version because it's a lot smaller. 3x over x plus 4. Get the y-intercept. Plug a 0 in for x. 0 on top. That's going to be 0, 0. Automatic. And then x-intercept. Just set the numerator equal to 0. Hey, there's only one. Because that's going to be x equals 0. And we know y is equal to 0. So the only intercept I have for this thing is the origin. It's 0, 0. It just happens to be the same order pair for both of them. That worked out really nice. Last thing to decide is, does it cross the horizontal asymptote? So we set, okay, does g of x cross y equals 3? And so you take your equation, 3x over x plus 4, and set it equal to 3. Multiply by x plus 4. You get 3x is equal to 3x plus 12. And lo and behold, we get the x's canceling out again, and 0 does not equal 12 ever, so this is no solution. So, no, it does not. Remember, if you get an answer there, then it does. If you don't get an answer there, it doesn't. It is rare that they cross, but it is something that can happen. Okay? All right? All right, so there's some suggested problems from 5.4 and 5.5. I don't know if those page numbers are 100% correct. That's what I've got written there, but I'm assuming I hope it's right. It's close. It's those sections. Those numbers should be sufficient for that. So this week, you'll have quizzes over 5.4 and 5.5, or this week and next week total. And then the Chapter 5 test will be available too. That stuff will be due on the 21st. We won't have class next week, so you will have 2 weeks to get this stuff, get this down and get practice, and we'll go through that practice test or the review for the Chapter 5 review. Go through it as many times as you need to. Email me. Even though it's fall break, I'm still working, so send me an email if you need some help with something or you're not figuring out what you're supposed to be doing. Don't feel like you're bothering me because I'm still at work. My high school fall break starts Wednesday. So I'm off Wednesday to Friday with them, and then you guys Monday and Tuesday. So I'm still at work really. So, but midterm grades are due this week by Friday. So whatever your grade is right now, that's what I'll put in to banner for midterm grades, which you guys are all doing fine. No worries about that. And we'll go from there. All right. Appreciate it, guys. Y'all have a great week. Enjoy fall break.